Am I audible? Can anybody please? Okay. Hi. First of all, I'm sorry for the inconvenience. Due to some technical issues, the internet was not working properly to the pen. Okay. So that's why it takes some more time. Sorry for the inconvenience. Okay. So welcome to the fourth live session of the Algebra 1. Mm, Before starting, first let me know, do you have any doubt or any questions, or do you want me to solve any mm, particular concept? Please ask. Do you have any doubt or any questions, or any confusions, or any? Do you want me to clear any particular concept? Okay. Mm, so mm, so in the second live session, some learner asked me to go with the mm, semi-direct product. Okay. So today I shall go with the semi-direct product first. Then, if time permits, we shall go to shallow theorem. Okay. And in between, if anybody have any doubt, any question from any questions, please ask me. Okay. I shall try to answer as much as possible. So first, let me know: is the screen visible to you? Is the screen visible to you? Okay. Okay. So first, let's start with semi-direct product. Sorry. So So basically, the what is the motivation of semi-direct product is to make make non-abelian groups. Okay. So under some certain conditions, I mean, in most of the situations, semi-direct product only gives the non-abelian groups, except some typical situation. Okay. So semi-direct product is a way to generate non-abelian groups out of given abelian groups. Okay. This is the first target which one can get in semi-direct product. Okay. So So, yeah, yeah, I understand that I should start with some problems, but on the second live session, some learner asked me to go with the semi-direct product full details. That's why I'm starting the semi-direct product from scratch. So let H and K be two groups. Okay, one second. And let phi K to odd H be a group homomorphism. Okay. Then consider this product H cross K. And here we can define a binary operation as follows. So while I'm writing on over the screen, I can't see actually the chat box. If anybody have any doubt, any questions, please unmute yourself and ask. Okay, because I could not really understand that. I mean, I can see the chat box, but then I have to stop and then open the chat box separately. Okay, so then please unmute yourself and ask. Okay. So on the H cross K, we can define a binary operation as follows: H cross H1 cross K1 dot H2 comma K2. We are
Excuse me,
defining.
sir. Please bring down the page once.
Yes, yes, sorry. Yes. Now is it fine for you?
Yes, yes, yes.
Yes. Okay. So we have two groups H and K, and suppose phi is a homomorphism, group homomorphism from K to aught H. Okay, and then consider the set H cross K, and on the set H cross K, we can define a binary operation as follows. That is H1 comma K1 dot H2 comma K2. We are defining at H1 of phi K1 H2 comma K1 K2. Okay. So this is the binary operation that we are following. Okay. So it is not difficult to check that this binary operation is associative. Secondly, this operation, um, sorry, first, yeah, this is associative, and then 1 comma 1 acts as identity in H cross K, and thirdly, uh, every element HK has an inverse, namely HK whole inverse 2.2. So firstly, it is you can check that it is associative. Also, 1 comma 1 acts an identity, and each element has an inverse given by this formula. Okay. So which are basically group properties. So that's why that binary operation makes H cross K a group with that binary operation, and we denote this group by H semi-direct. I mean, it is a product but not full, and phi is written on the bottom of this notation. H semi-direct K, and it is abbreviated as semi-direct product of H and K. Okay. Yes. Yes, Ashutosh, please ask. Ashutosh, yeah. Please tell me.
Yes, sir.
Yeah. Please tell me.
Sir, little handwriting.
Sorry. Can you? I could not. I could not.
Sir, I am confused in handwriting.
Oh, sorry, sorry, sorry. On which portion you got the confusion? Okay, so the thing is, first H and K are two groups, and we have phi from K to outage is group homomorphism. Okay, and then on H cross K, we define a binary operation as follows: that H1, the definition is as follows: H1 K1 dot H2 K2 is defined as H1 of phi K1 H2 comma K1 K2. Okay, this is the this is the definition of binary operation that we have taken chosen here. Okay, and it is easy to check that this binary operation is associative. 1 comma 1 acts an identity in H cross K, and every element of every element H comma K has an inverse H K whole inverse equal to phi K inverse H inverse of this. Okay, phi K inverse of H inverse comma K inverse, and with so these are the properties satisfied by a group. Okay, so under this binary operation, this H cross K forms a group and is denoted by H semi-direct K. Basically, the notation is this, and is denoted, and it is called as the semi-direct product of H and K. Okay, this is the definition of semi-direct product. Do you understand?
Point number three, once clear now.
Point number oh, yeah. So point number three says that every element has an inverse. Every element of the form h comma k has an inverse of this form. This basically you can check that this thing phi k inverse of h inverse comma k inverse is an actual inverse of h comma k under that binary operation. Okay, please check that whether this works or not. I mean, point number three basically tells about the existence of inverse. Okay, that's it. So, in order to check the inverse, what we will do? So, h comma k dot phi k inverse h inverse k inverse. This is what? This is h by definition phi k of phi k inverse h inverse comma k k inverse. This is h phi. Since phi is a homomorphism, so k k inverse comes together. It acts on h inverse comma k k inverse. K k inverse is 1. Okay. H phi of 1 h inverse comma 1. And phi 1 is an identity automorphism, so it is h, sorry, it is not comma. Okay, h inverse comma 1, which is nothing but 1 comma 1. So this thing is actually an inverse of h comma k. Okay, so that's what is nothing but the point number 3. You understand? You understand? Please let me know, do you understand? Okay, so I hope you understand. Okay, so h cross k, finally we get h semi-direct k is a group. That's the thing firstly. Okay, now what are the elements of the, I mean, what are the elements, what is the form of the elements of h semi-direct k? H cross k. Okay, sorry, h comma k. Now consider h delta, nothing but h comma 1, h belongs to h, and consider k delta, which is k, sorry, which is sorry, consider k delta, which is 1 comma k, k belongs to k. Okay, check that h tilde and k tilde are subgroups of h semi-direct k. Kindly check. Please take your time and please check that h tilde k tilde are both subgroups of h semi-direct k. Okay, please check. If at any portion, if you have any confusion in understanding some definition of some lines, please ask. Unmute yourself and please ask. Please check that h tilde k tilde are both subgroups of h semi-direct k. Have you checked that H tilde K tilde both are groups? If you have no doubt, please ask, but please don't be silent. If you are not getting this definition or these things inside the similar product, please ask. Plus, but please don't be silent. Okay. I hope you have checked that H tilde K tilde are both subgroups of H. Okay. Also, uh, check that H tilde isomorphic with H and K tilde isomorphic with K. By the obvious map, H comma 1 goes to H and 1 comma K goes to K. Please check the whether this is isomorphism or not. Please check.
Sir, I have not understand the better. There was a background sound is coming.
Oh
Uh,
yes, 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 yes. So basically,
uh,
the main target of the going on to yeah. So basically, the main target of doing the seminar product is that by using the techniques in the seminar product, we can generate uh, non-abelian groups as many as we can. Okay, and also in terms of classification problem, seminar product comes into the role because of the non-abelian groups. Okay, so I mean basically the seminar product tells that under certain conditions any group can be written in terms of seminar product of some groups. Okay, so that's why the seminar product is important. It is a tool which solves some problems. So that's why you need to study the seminar product. Okay, and in most of the situations seminar product gives non-abelian groups only except certain conditions. So that's why in order to get non-linear groups as many as we want, we need to study the semi product. Okay. And do you understand the target? So what we have done so far, we have taken two random groups H and K. Okay.
Sir,
Yes. Yes.
which book we refer for that part?
Sorry. Can you please repeat?
Which book we refer for that?
Can go Damit put.
One
Damit
second.
and 1 minute. Let me write down the spelling.
Book का नाम है
Yes. X 1 second. Writer name is Damit and put. Astronaut. Okay, this is the book. I mean, you can find it in the standard text also, but this book has presented it in some very good way. That's right. Understand?
Yes, sir.
Okay. So far what we have done. So so we have started with two groups H and K, and we have chosen an automorphism phi from H to or H. Okay. Sorry, it is a group homomorphism we have taken. And then on H cross K, we are going to define a binary operation as follows. I mean, given by this following equation. Okay. And it is not difficult to check this binary relation satisfies the three property of group. So under that binary relation, H cross K become a group, and we denote this group at H semi-direct K. Okay, by this notation. And obviously phi is necessary here because phi is the map from K to hot H. Okay, so this is the semi-direct product of H and K. Right now, just yeah, right now the thing is that if you take any random group H, any random group K, even they are abelian, but the semi-direct product is most possibly non-abelian because there are very few conditions under which the group will be abelian. Okay, so that is the main advantage of semi-direct product. Because if you consider direct product, so direct product abelian group is always abelian, but in the semi-direct product, this is not the case. Okay, so that's why we need to restart the semi-direct product. This is the first motivation. Okay, so so soon we will prove that. Okay, what are the conditions under which the semi-direct product will be abelian? Soon we will. So for this, we go to step by step. So first observe that consider two sets H tilde and K tilde inside H semi-direct. H tilde is given by H comma 1 and K tilde is given by 1 comma K. And please check that these two sets H tilde and K tilde are basically subgroup of H semi-direct K. Please check that these are subgroups. Please try. I will do also. First you try please. Using that definition definition of binary. Sorry, I mean using that binary operation. Please check that H tilde and K tilde are both subgroups. Please take it back. If anybody of you is not getting it properly, please ask. Just please don't be silent. Please check first that H tilde and K tilde are both subgroups. In between, if anybody will doubt in the binary operation itself or not getting it properly, what is going on, please ask. Don't be silent because this session is meant to clear doubts, concepts, etc. So please utilize it.
Sir, please bring down the page uh, slightly.
It's fine.
Okay. Fine.
Yes, yes. Please check that this H3 and K3 are both subgroups. Have you checked that H3 and K3 are both subgroups? Okay, so let's check it. So how to check the subgroup condition? So we take two elements H1, comma 1 and H2, comma 1 inside H2. So what we will do, H1, comma we will check that H1, comma 1 and H2, comma 1 inverse belongs to H delta or not. This is what we need to check. Correct?
Yes.
So firstly, what is H2, comma 1? It's inverse. By definition, it is phi of, and by the formula it is phi of 1 of H2 inverse, comma 1. Correct? Phi of 1 is the identity automorphism. So basically it is H2 inverse, comma 1. Okay. Now H1, comma 1 dot H2 inverse, comma 1. This is what H1 phi 1 H2 inverse, comma 1. This is what? This is H1. Phi 1 is identity automorphism. So H1 of H2 inverse, comma 1. So in this is obviously this belongs to H. Okay, because it's a subgroup H tilde. So that's why H tilde is a subgroup. Sorry, is a subgroup of that semi-direct product. Understand?
Yes.
So similarly, we can check that K tilde is a subgroup of H. It is exactly similar process. Okay. Now we're claiming that H tilde not only subgroup, H tilde is actually a normal subgroup of H semidirected. Okay. So for this, what we will do? So we can directly check the normality by using the usual definition. Else we can construct a map from H semi-direct K to some other group whose kernel is H tilde. Okay. So this is another way. So we will use. I mean, it can also be done in that way, but we will use that mapping way. Okay. So okay. So let me repeat. So normality can be checked in two ways. First, using definition, or secondly, we can construct a map F from H semi-direct K to some other group whose kernel is H tilde. That way, that also tells that H tilde is a normal subgroup. Okay. So, so what we'll do, we can define a map from H semi-direct K to K. Consider projection of H comma K goes to K. Okay. It is not difficult to check that this F is a group homomorphism and surjective. Okay. And obviously kernel F is equal to H comma 1, which is nothing but H tilde. Okay. So H tilde is basically normal subgroup of H semi-direct K. Do you understand that why H tilde is the normal subgroup?
Sir, you have told that there are two ways to show a group, giving group is normal subgroup of some homomorphism. So in which one is literal definition we have to show,
Sorry,
or
can you
otherwise,
please can you please repeat? I could not hear properly actually.
uh,
Please repeat.
you have told there are two kind of ways to show a given group of some homomorphism. It is a normal subgroup or not. So one definition is using that same definition. Otherwise, we have to establish a homomorphism and showing its kernel should be that. Hmm. Second, hello.
Yes, yes, please tell.
Uh,
No, no, I mean using the definition of normal, we can check it also. And another way is
hmm.
doing the getting construct some map from H semi-direct K to K and such that its kernel is H tilde. This is another way. Okay. So in these two way we can check the normality.
Hmm. Okay. Kernel should be the image of the homomorphism.
Kernel, sorry, kernel.
Here kernel is I'm not clear the point.
Okay, so the thing is, so you know that kernel is or kernel always be normal.
Normal subgroup. Uh,
Yes, so I'm using that fact. So we have constructed a map from H semi-direct K to K, whose kernel will be the H tilde. This is what we try to show. Okay, I mean these are target.
oh, okay.
So we have taken the second coordinate projection map. Firstly it is a group homo surjective, and kernel of this map is H tilde. So that's why H tilde is semi-direct product of H. Sorry, H tilde is, yeah. What is that? Normal subgroup H semi-direct K. Okay, understand? Understand? So A still takes uh, normal. So, hmm. So okay. So consider the following example first. One second. So consider the first example. Hmm, take H equal to Z. Okay, and K equal to, and take the map phi from Z2 to odd Z. Firstly, what is odd Z? Anybody please? It has to be a homomorphism. Anybody please tell what will be odd Z?
Sir, isometric to Z not fusion.
So that is just two elements. Okay. So the one will be the identity and another will be x goes to x inverse. Okay. So this homomorphism phi is to do this. 0 goes to the identity automorphism and 1 goes to the map x goes to x inverse. Okay. So now then consider this semi product. This. Okay. So the claim is that, I mean, so this is the group and claim is that with respect to this file, this thing is nothing but the, yeah, sorry, put h equal to z or z. Also difficult one. Sorry, it will be actually difficult this time. Good.
Sir, I Z to automorphism of Z after that Z2.
I'm trying to get some example.
Okay.
I've written a bit wrong actually. Sorry. Just hold on. Yes, what you have said, please repeat again. What you have said, please repeat.
Sir, I Z2 to automatism of Z. After that, in between the which sign or or Z and Z2. In between this,
Basically, the target is that we are trying to get the dihedral group from the standard drug. Okay, so and for that we need to somehow match with the cardinality. First we need D4. Okay, cardinal D4 is 8. Okay, so somehow we need to come up with the Z4 on the left side. That is what we are trying to do. But somehow it is not coming. Okay, sorry for the inconvenience. Please hold on, we shall get back to the example. Okay, okay, so um, okay, so there are some criteria under which that I mean there are some criteria which usually does not occur frequently, and under that criteria the group will be actually an available group. Okay, okay, so before going further, just observe one thing, that two subgroup H tilde and K tilde, their intersection is 1. Okay, and H tilde is normally the semi-direct product. Okay, now so the following are equivalent. Firstly, the identity map from H semi-direct K to H cross K is group homomorphism. It is equivalent with the fact that phi is trivial homomorphism from K. And thirdly, K is normal subgroup of H semi-direct K. Okay, so these are the some equivalent conditions. So I mean, though these are easy, but let's prove it first. So first of all, what I assume that identity map is a group homomorphism, and we need from this we need to show that phi is a trivial homomorphism of K to auto H. Okay? So this implies what? This implies H1 comma K1 dot H2 comma K2 ID of this thing. Since the group homomorphism, this will be equal to ID of H1 K1 dot ID of H2 K2. Okay. Remember the left side is the semi-direct product and right side the direct product. So what will be this? It will be H1 phi K1 H2 comma K1 K2. This is equal to H right side direct product, so H1 H2 comma K1 K2. Okay. Then this holds for H, all H1 H2 belongs to H, and for K, all K1 K2 belongs to K. Okay. So this implies what H1 phi K1 H2 is equal to H1 H2. So we can cancel H on both sides and get phi H1 phi K1 H2 is equal to H2. And this holds for all H2 belongs to H, for all K belongs to K. This implies what? Phi K1 is trivial for all K. This implies phi is trivial homomorphism. Do you understand? To understand the first proof that identity map is proof homomorphism plus phi is trivial homomorphism.
Yes, sir. Sir, sir, in semi-direct product,
Yes.
so all the elements cannot be zero.
Sorry, already. Why? Why you think so? I mean, first of all, it's a group, right? So, I mean, if the both groups are trivial, then it's obviously trivial. Otherwise, it depends on the phi. If the phi is trivial, then some elements may be trivial, but all elements can't be trivial. Okay, so in any case, immediate product is non-trivial. Okay. And now we shall prove that from 2 to 3, which says that phi is a trivial homomorphism, and third is that K is a normal in H similar to K. Okay. So assume that phi is trivial, and then we check that K is normal subgroup H similar to K. Okay. So what we will do? We will go with the yeah. I mean, here we can. By the way, here I have written K is normal H similar to K, but K is not even a subgroup of H similar to K. Okay, I mean it is not inside the element. So by K we mean K tilde mostly. Okay, so we need to check that K tilde is normal in H similar to K. So what we will do? Same technique. We'll define a map F from A from H similar to K to H first corner projection, and if homomorphism, and the kernel of F is equal to K tilde. So that's why K tilde is normal in a similar K. Mind it, here if we are group homomorphism, because on the fact that phi is a trivial. Okay, that's why if is a group homomorphism. Here you can check also. Okay, so this is the 2 to 3. Now, yeah, and also, yeah, we have already proved 1 to 2. Okay, and 2 to 1 is exactly same direction. Okay, and 2 to 3 we have just proved. And please think about how to prove from 3 to 2. Okay, it is very much it. That's why I'm not right now. I'm not doing the full thing. Okay, so these are the some equivalent criteria. First criteria is the identity map is a group homomorphism. The second criteria is that right group identity map group homomorphism if and only phi is trivial map. One second. And thirdly, the subgroup K is normal. In general, we have already H is normal, but in this situation, under this criteria, K is a normal subgroup. Okay, so these are criteria. These are some criteria. Okay, for it to be H cross K. So the advantage is that if somehow we can find that H is normal in H is semi-direct K, then immediately we can say that semi-direct product is isomorphic with the direct product. So then only it will be abelian. Do you understand? Okay, I am sorry. So now there is one fact is that okay. So now let's see how powerful this equivalent criteria is. Okay. So suppose you have some group G. Okay. One second. What is need to just hold on. Okay. So before doing this, there is another theorem. We need to go with this first. So this the upcoming theorem tells that any group can be written as a semi-direct product of two of its proper subgroups under some certain conditions. Okay. So what is this theorem? Suppose G is a group and H, K are two subgroups of G, such that H is normal in G. Secondly, the intersection is identical. Okay. Now define MF phi from K to aught H by phi K H to be the inner automorphism K H K inverse. Okay. This thing belongs to H as H is normal in G. Then H cross K is isomorphic with a semi-direct product H. That's okay. Okay. This is the first thing you need to observe. Yeah, this is the statement. So what this tells? This tells that if we have a group G and suppose H and K are two subgroups, they such that H same is normal in K and H and in case 1. Then we can define a map phi from K to out H, phi KH and KH inverse, and then H comma in H the internal direct product of H and K is isomorphic to the semi-direct product. Okay, so this is the theorem. So how to do it? Since are already given that H is normal in G, so this implies HK is already a subgroup of G. Okay, and since intersection is 1, so the elements of HK has unique representation. Okay, now so unique representation. So we can define a map HK to a symmetric phi from H cross K H comma K. Okay. Now first, now kindly check that this is a group homomorphism. Please check that it is a group homomorphism. Okay. Please take your time. I shall, yeah. Please check. I shall come back after 2 or 3 minutes. অ্যান্ড্রয়েডে বন্ধ হয় মাঝে মাঝে ভুলে যাই Have you checked that HK and that map is group homomorphism? Have you checked?
So, what are the operation in the product group instead?
Uh, Sorry, I didn't get you. Can you please repeat?
Sir, the operation in product group explore. What are the operation?
Uh, yes, operation will be operation on the which side? Left side. I mean, yes, left
Yes,
side
sir.
is sorry. Left side is HK. Sorry, extremely sorry. Yes.
Sir, if we take any two element in the product group actually, so how do we operate? That means we are in point-wise multiplication.
Yes, I understand. So basically, your question is that how two elements H K and H dash K dash, how this will look like of the form H cross K, right?
Yes, sir. What are the operation? Sir, that the form of group.
Oh. So the fact is that since H is normal in G, then this tells actually that HK is a subgroup. Okay, so use a normality. So we take two elements H1, K1, H2, K2. Okay, so we already uh, yeah. So yeah. So we know that H1. Uh, so this we know belongs to capital H. Okay, K1. Sorry. What's the element? Hold on. Since H is normal, so mm, so HK is equal to KH. Okay. So this implies what? For all H belongs to H, right? So this implies H1 K1 is equal to some K3 H1, right? So this thing can be written as K3 H1 H2 K2. So this thing is K3 some H prime some K2. Again, normally this will be H prime K4 K2. Yeah, this is the operation. I mean, in this way, we can write this. We can write it like that. Okay? And actually, for due to this reason, in each step we have to check that whether that map is a group homomorphism or not. Okay. Directly, it is not possible to check. So I mean, yeah, you can check in your free time that this will be a group homomorphism. Okay. So and obviously it is an isomorphism. So I mean, it's obviously bijective. So it's an isomorphism. So what I've seen that if H and K, H if H is normal in G and the intersection of H and K is 1, then under that um, homomorphic phi, HK is homomorphic isomorphic H semi-directly, okay? And moreover, if um, the in G is equal to HK and H semi-direct, say H is normal in G and intersection empty, then G is isomorphic to H semi-direct product, okay? So this tells that under certain conditions, G is isomorphic to the semi-direct product. So what is the moral of the story? Moral of the story is suppose G is a group and suppose H is a normal subgroup of G, and suppose the intersection of H and K is identity. Now, if H is the internal direct product of H and K, then actually H will G isomorphically the semi-direct product of H and K for some phi. Okay, this is the advantage. So, and so this actually also tells that in general H comma K is not abelian. So, in which situation this will hold? This situation is likely to hold mostly in finite groups. So, this is the first important result that we need to understand. That suppose G is a group and H is normal subgroup of G and the intersection identity. And if G is the internal semi-direct product, then G is the internal direct product of H and K, then G will be the semi-direct product of H and K. So this is the thing that we want to discuss. So okay, so I think some of you had lost it actually. So okay, so let me repeat. So first theorem was that suppose G is the group and H and K are two subgroups of G, okay, such that H is a normal subgroup of G and the intersection of H with another subgroup is identity. Then we can define a map phi from K to aught H by giving the inner automorphisms. And under that inner automorphism, under that phi, HK, the internal direct product, isomorphic to semi-direct product. And moreover, if G is the internal direct product of H and K, then G is isomorphic to the semi-direct product of H and K. Okay, this is the fundamental thing that we want to know. Okay, so yeah. So till now, do you understand that chronology? In which direction are we going? Or in confusion, please ask. Don't hesitate. Please ask. Don't hesitate. Till now, do you understand what is going on, or you might have lost it? Please ask. Okay. One second. Okay. So now let's go that example in which we started stuff. Okay. So let H be an abelian group and K is equal to 1, X be another group. And define a sigma from H to H goes to H inverse. Sigma is an element, is an automorphism of H. So now define a map phi from K to out H in obvious way by sending x goes to sigma, and then define the similar product given with phi. Now take h comma 1 belongs to h tilde and x equal to 1 comma x belongs to k tilde. H comma 1 we are writing for the convenience as h. Okay. Now what will be the x inverse? By definition this will be 1 comma x h comma 1 1 comma x 4 inverse. This is 1 comma x h comma 1 1 comma x inverse. So this is nothing but h inverse comma x comma 1 comma x inverse. So this is nothing but h inverse comma 1, which is nothing but h inverse. So this gives that x inverse is equal to h inverse. This is one relation. Okay. Now if we take h equal to zn, okay, now then order of h will be what? It will be n for some h, and we have taken k to be z2. So the group H semi-direct will be what? This will be generated by third bracket 1 comma x, such that order of third bracket 1 is equal to n, order of x equal to 2, and the relation x inverse is equal to h inverse. Okay, and this is the representation of what? This representation of D2n, dihedral group. So the dihedral group can be represented in terms of the semi-direct product. Okay, so these are examples. First we work this. Please go through the example once again and let me know if any doubt or confusion. If you ask me to repeat, I will also repeat it. So no questions, okay. So okay, so I think today we should not go further with the similar product. Please uh, take your time to understand similar product. Okay, please go through the proofs and the theorem, and also from the Damit book, Damit code, please go through the examples. Okay, so that you can understand how the operation is acting here. Okay, so for today, let's stop the seminar plot here. Now we shall start with the Shiloh theorem. Okay, I mean Shiloh theorem or any topic which you ask me to go with. So please tell which topic I should go with, or should I start some problems from the Shiloh theorem? Let me know. Sorry, your voice is breaking. Can you please? Uh, clear?
So, we discuss more earlier.
Mm, uh, can you please type in the chat box?
Okay.
There's a chat box. Yes, yes. I discussed the group action earlier. Okay, mm, okay, so since none of okay, how to extend 1 second. Let me think. Let me recall it. So, basic group action and some examples of the actions which will be later used with the style of theorems. Okay. Okay, so that's fine. So let's continue the group action. So first, let's go with the Burnside lemma. So does anybody know about the Burnside lemma in the group action, or anybody heard about the name, the Burnside lemma? Anybody heard the name Burnside lemma? Okay. Okay, silo theorem related problems. Okay. Okay, so silence. Okay, that's fine. So basically, Burnside lemma. I mean, first comes Burnside lemma, then comes the class equation. But since you are suggested silo theorem related problem, so let's start with the silo theorem problem. So, can anybody please tell the class equation? We shall go with the Burnside lemma the next class. Okay. First today is with the silo theorem problems is as some of you suggested. So please anybody tell the class equation. Please anybody explain the class equation. Okay, so basically the class equation is suppose G is a finite group, then order of G is equal to order of ZG plus summation G by order of CXI, the finite summation. Okay. So this is the class equation. Order of G is equal to order of ZG plus summation X does over ZG, order of G was CXI, CXI means centralized. Okay. So the first application is okay. So for example, how to use it? For example, take the abelian group Z4. What will be its class equation? 4 is equal to 4. This is the classification. Okay. So consider the group S3. What is the classification? First, 6 equal to, what is ZS3? ZS3 is equal to 1. Is equal to 1 plus. Now, observe something that in the classification formula, ZG is a subgroup of G, and also CXI is also subgroup of G. So order of CXI divides the order of G. So order of this thing, so order of G by order of CXI, it also divides order of G. Okay. So whatever the right side, it has to divide on the left side. I mean the order of G. So 6 equal to 1 plus something. Now something has to give the sum total 5, and each of which has to divide 6. So only one possibility is 2 plus 3. So this is the class equation of S3. Do you understand how we have calculated the class equation of S3? Do you understand? Please don't be silent.
Please repeat.
Sorry, can you please repeat? Yes, yes. So one of, yes, yes. I'm giving the answer one way. So first of all, one of asked that if order of G is given, how to write its class. Okay. So okay. So I thought that you know what the class mean, but anyway. So basically, uh, so just G is an element, and suppose X belongs to G. By class of X means the third bracket X. We mean the all possible conjugates of X. This is denoted by class of X. Okay, class of X is the set of all uh, conjugates of X. Okay? And the class equation was initially like, look, like order of G is equal to order of ZG plus summation all those X which does not belong to ZG, order of class X. And we can, and later we have proved that order of class X is nothing but order of G, the order of CX. Okay, this is the fact, and this is the thing. By class for element, we mean the collection of our conjugates. Okay, group does not have any class. Class has only, I mean, elements does have only class. I mean, this makes sense only. That's the point. Okay, and CXI. No, no, oh, CX. Sorry, CXI means centralizer. Okay, so first tell me one thing. Some of you have told that with the Silo theorem. So, don't you know class equation? I mean, have not you seen the class equation before? How many of you have not seen the class equation? Please raise your hand. Okay, yeah. What about others? Only there is one person who don't know the class equation. What about others? Okay, since, okay, so Okay, so first let me register the classification clearly. Okay. Sorry, one second. The application is not. Okay, so the screen. Okay, I understand how it works. Okay. So can you see the screen? Are you able to see the screen? Please type in the chat box. Okay, so okay. So start the classification. Since some of you don't know, so I am starting from scratch. So let G be a group. Let X be an element of G. Okay. By class of the element X, we mean the collection of all elements G, X, G inverse, G. Then we have the following equation or the class equation, that order of X, and also it can be shown that class of X is isomorphic to G by Cx. Cx means centralizer of X. Then we know the following: order of G is equal to order of JG. It's a class equation. We're not going to prove it right now. So order of G is equal to order of JG plus summation X does not belong to JG, order of G by order of Cx. I mean, we are collecting the all elements which are in the center together, and then for each of these elements which is outside the center, we are getting the summation order of G by order of Cx. Okay. Now, yeah. So this is the classification. So first, what is the first application? Suppose G is a group and order of G is P2 over N. Then order of ZG has to be non-trivial. So as a first application, so if G is a group order P to the power N, then order of ZG will be non-trivial. No, I mean the ZG will be not non-trivial. Okay, so this is the first application of this. Now how can prove this? So now consider the classification. Order of G is equal to order of ZG plus summation the rest of the portion. Now observe that P divides order of G, and since X does not belong to ZG, okay. Now for X does not belong to ZG, centralizer of X is a proper subgroup of G. Okay. So order of Cx, this is strictly less than equal to P to the power n minus 1. Okay. So this implies P divides order of G by order of centralizer for X does not belong to ZG. So in this equation, P divides the order of G and also P divides the right hand side summation portion only. So obviously P divides this portion. So P divides order of ZG. So this tells that order of ZG is greater than 1, that is non-trivial center. So yeah. So do you understand the proof?
So one line I can understand this is centralizer of X for
Yes.
put a subset of G and after that centralizer of X the cardinality less than equal to 3 minus.
Yes. If X is an element outside the center, then its centralizer will be strict will be proper subset of G, because if centralizer proper central is equal to center, right? So central is a proper subset of G. So order of centralizer is strictly less than equal to P to the power n minus 1. Okay. So
Mm-hmm.
in G by Cx, we have at least one factor of P. But I mean, G by Cx will be P to the power something, but something will be, I mean, G by Cx will be at least P to the power x, where x is strictly greater than equal to 1. So that's why P divides the G by Cx side for all x belongs outside the center. Okay, understand? Do you understand?
Yes.
And this means that P divides order of Z. Okay. So now, so we have seen that if a group is order P to the power n, so its center is not real. So second corollary is that if a group of order P square implies G commutative, it's a very powerful thing. Any group of order P square must be commutative. So can you please solve it? We have already proved that order of G is greater than P, right? So order of ZG is either P or P square. Now show that order of ZG can't be equal to P. This is not the case. So please try that why order of ZG can't be equal to P. Please think about it. It is a very basic property in the quotients. Let's take it time. Sorry, in the normal values. Check that y order of ZJ can't be equal to P. Please think about it. I shall back up to 2 minutes. So have everybody got the answer why the order of ZG can't be equal to P? So I mean, so if order of ZG is equal to P, this implies what? Order of G by ZG, which is P, will be a prime. So in that case, G by ZG will be cyclic. So this implies what? G commutative. But this is not the case because we have assumed the order of G is equal to P and G will be of P square. So order of ZG can't be equal to P. So order of ZG has to be equal to P square. So this implies G commutative. Do you understand argument? Do you fully understand argument? Do you fully understand the argument? Okay, so one thing and one second. So another corollary we can say that if G is a group order P to the power n, then it has a normal subgroup of order. Please think about it. G is a group order P to the power n, it must have a normal subgroup order P. So till now what we have proved two results. If G is a group order P to the power n, then its center will be non-trivial and also group order P square will be commutative. Now try to show that if a group order P to the power n, then it has a normal subgroup for order P. Here you need to use the fact that for a group order P to the power n, its center is not trivial. Use it and try to solve this. Please solve. Anybody found the answer why it will be normal subgroup? Okay, so the answer is simple. That since G is a group, so order of Z is anyway. Okay. So, uh, so P divides order of Z. So this implies there exists a subgroup H with order of H equal to P, and H is contained in such H. Now since H is contained in Z, this implies what? It implies GH equal to HG for all G belongs to G. This implies H is normal at G. So this tells us H is normal subgroup, and by choice order of H is equal to P. Do you understand? So first we have used that for a group order P to the power n is centered will be non-trivial. So P divides that order of G. Then since P divides the order of ZG, so we must have some H with order of H equal to P, and it is subset of ZG. This tells that GH is equal to HG for all G belongs to G. And this tells that H is normal in G. Okay. So this tells that it is a subgroup of, it has normal suborder. Yeah. So, okay. So, some of you has, let me check. Okay, some of you have the silo after silo here. Okay, so first let me start the statement of the silo here. Three statements. First of one, if G is a group and order of G is equal to P to the power n into M, if GCD Pm is equal to 1, then for each I with 0 less than equal to I less than equal to N, G has a subgroup H with order of H is equal to P to the power I. This is the first statement, and additionally subgroup of order P to the power n called child of P subgroup. Okay. Second statement is that any two child of P subgroups are conjugate. That is, if H and K are two Shiloh P subgroups, then there exists G in G such that K is equal to GHG. Okay. Sorry. And third statement is that if NP is equal to number of Shiloh subgroup of G in H, then NP is equal to KP plus 1 and NP divides order of G, where K belongs to natural. These are three statements of the silo theory. Okay. So, mm, okay. So, using this, so first proof that its application group of order 15 must be cyclic. No, sorry. Before this, there are some corollaries actually. So, if H is unique normal, this for that if H is a normal Shiloh-P subgroup, then H will be unique and vice versa. So basically, normal Shiloh-P subgroup, the unique must be unique. That's the point. Okay. So how to prove it? Suppose K be another Shiloh. No, sorry. So thing is, take G belongs to G. Then consider G as G inverse. Now, G inverse is also a Shiloh-P subgroup, right? But this is equal to H because H is normal in G, and if K be any Shiloh-P subgroup, then K is equal to G inverse for some G. So this has to be equal to H. So this tells that normal Shiloh-P subgroup has to be unique. So basically, what is the argument? If we take any arbitrary Shiloh-P subgroup, then it will be conjugate of H. But since H is normal, so conjugate of H is equal to H itself. So that's why any randomly taken Shiloh-P subgroup is nothing but equal to H. So this is the argument. Do you understand? Understand? Please don't be silent. Please let me know if you have any doubt. Okay, why it is true? Definitely. Yeah, I mean, there is a okay, so I thought you know the Cauchy theorem. One second. So yeah, so it seems that you don't. Some of you might not have idea the Cauchy theorem. So the student of Cauchy theorem as follows. Sorry. So a Cauchy theorem tells that if P is a prime, divide the order of G, then there exists an element in G of order P, and hence G as a subgroup of order. So this is a Cauchy theorem, and due to this we have that thing. Understand? Okay. So yeah. So first thing Cauchy theorem tells that normal subgroup is unique, and similarly conversely unique Shiloh subgroup must be normal. Okay. So okay now Now the fact is that if G is a group, order G is 15, then G cyclic. Okay, how to solve this Silas problem? So 15 equal to 5 into 3. So NP divided number of silos are N5 divided number of silo 3 silo 5 subgroups, N3 divided number of silo 3 subgroups. Okay, and by silo theorem, N5 is equal to 5k plus 1 and N3 is equal to 3k plus 1, and both divides order of G. Now what is the factor of G? 1, 5, 3, 15. Now 5k plus 1 can be either 1 or 5 or 3 or 15. Okay. Now 5k plus 1 can't be 15, obviously it can't be 3, can't be 5. So it has to be equal to 1. So 5k plus 1 has to be equal to 1. So N5 equal to 1. So it has only one silo 5 subgroups. What about N3? N3 equals 3k plus 1. It will be either 1 or 5 or 3 or 15. Okay. 3k plus 1 will be odd, even number, right? So it can't be equal to this thing. So N3 equal to 1. Okay. So N5 equal to 1 means it has unique silo 5 subgroups, which is normal in G. And N3 equal to 1 means it has unique silo 3 subgroup, which is also normal in G. And also order of HK is equal to 15. So basically G is equal to HK. And also they are normal in G. And since their order is 5 and 3, so intersection is also 1. So in that case, internal direct product is isomorphic to external direct product. So G isomorphic to H cross K. H is Z5 cross Z3, which is nothing but Z15 because this is 5 and 3 is 1. So G is cyclic. So this is one nice use of Silas theorem. Do you understand? So okay, so let me repeat what I've done. We have started with the group order 15, which is cyclic. Okay. Now with 15 is equal to 5 into 3. Okay. Now we need to check number of silo P subgroups as well as um, as well as number of silo 5 subgroups. Okay. Now by Silas theorem, both divide order of G. Now N5 is equal to 5k plus 1 by the Silas theorem. So 5k plus 1 will be either 1 or 5 or 3 or 15. But obviously 5k plus 1 must have to be 1. Okay. So this tells that it has only one child of 5 subgroups. And similarly, you see that N3 is equal to 1. That means it has only one child of 3 subgroups. Okay. So it has only one child of 5 subgroups, only one child of 3 subgroups. Means these are normal subgroups of G. And by constant order, we get the G is equal to HK. And since one of the order is 5 and the 3, so intersection is 1. So basically, G is isomorphic to external direct product H and K isomorphic to H cross K, which is Z5 cross Z3, which is Z15. So that's why group G is, or group order 15 is cyclic. So the generalization is that if G is a group order PQ, PQ prime, suppose P greater than Q, and Q does not divide P minus 1, this implies Z is isomorphic to ZPQ. This is a generalization of the previous thing. Okay, exactly in the previous solution. Here also the exact way we can prove that G isomorphic to ZPQ. Understand? So this is the one nice application of Silas theorem. Okay, there are many applications of Silas theorem, but for today let's end here. Um, if you have any doubt, please ask me. Also, in the chat box, I've shared the attendance sheet to the link. please kindly submit your attendance by submitting the Google form. Okay. If you have any question, please ask. Also, kindly submit your attendance. If you have any doubt, please ask. Please feel free to ask doubts. Also, you can please kindly read the simulated product as well. If you have any doubt, please you can ask me in the next live session. Okay? Also, kindly give the attendance. Okay, so no, no. In general, HK is not abelian, but if the H intersection K is identity and both are normal subgroup, then only HK will be abelian. Okay. Only the intersection has to be identity in order to guarantee the abelianness. Okay. Okay. So. Okay. So since you seems to have no questions, so I am ending the session here. See you in the next week. Thank you.